How do pipes with holes make such magnificent sounds? As we shall discover in this section, many musical instruments produce their melodious sounds by creating standing waves inside pipes or tubes. Sound waves are an important kind of wave. Sound waves are longitudinal waves produced by the compression and expansion of the medium in which they propagate. As a tuning fork vibrates, its tines compress the surrounding air every time the fork's tines move out. Thus, their speed depends on the properties of the medium. For sound waves in a gas, such as air, the speed depends on the density and pressure. For example, sound travels much faster through helium than air because helium is much less denser than air. That is why your voice squeaks when you talk after inhaling helium. Sound also travels faster through air at warmer temperatures. Sound can travel even faster in media such as liquids and solids because they are much less compressible than gases. Under normal conditions, the speed of sound traveling through the air can be approximated from the temperature of the air. What is the speed of sound through air at a temperature of 15 degrees Celsius? Correct. The answer is 340 meters per second. The speed of sound through air at ambient temperatures is about 330 to 340 meters per second. The amplitude of sound waves is usually indicated by the amount of air motion or the change in air pressure associated with the wave. Some musical instruments, such as the pipe organ, produce sounds by creating a standing sound wave inside a tube. If the end of an organ pipe is open, sound waves are free to move past the pipe's end, but the pressure at the open end is fixed at atmospheric pressure. Thus, the open end of an organ pipe is an air motion antinode, but a pressure node. Because the distance between two antinodes is equal to half a wavelength, the fundamental frequency of the open pipe is equal to the speed of sound divided by twice the length of the pipe. An organ pipe with a closed end restricts air motion and causes pressure to build. Thus, the closed end is an air motion node and a pressure antinode. Because the distance between node and the adjacent antinode is equal to 1/4 a wavelength, the fundamental frequency of the closed pipe is equal to the speed of sound divided by 4 times the length of the pipe. Assuming the speed of sound is 340 meters per second, what is the fundamental frequency of a closed-end organ pipe that is 50 centimeters long? Correct. The answer is 170 hertz. Have you ever noticed how the frequency of the sound of a passing vehicle changes as it passes? This change in frequency is called the Doppler Shift. Consider an observer at rest listening to the sound of an idling car. When both the observer and the car are stationary, the sound frequency heard by the observer is the same as the sound frequency emitted by the source. Consider the case where the car is moving toward the stationary observer. The wavefronts of the traveling waves moving out in front of the car are compressed. As a result, the wavelength of the sound heard by the observer is shorter than that emitted by the source. Just how much shorter depends on the speed of the source. Therefore, the sound frequency heard by the observer is greater than that of the source. Consider the case where the car is moving away from the stationary observer. The wavefronts propagating back from the car are farther apart. The wavelength of the sound heard by the observer is longer than that emitted by the source. Therefore, the sound frequency heard by the observer is lower than that of the source. If the source nears or exceeds the speed of sound, the effect of the Doppler shift is extreme. As the source approaches the speed of sound, the waves are increasingly compressed by the plane until, at length, all the waves lie together. If the source continues to increase in speed, new sound waves will be positioned in front of earlier ones, and a cone-shaped shock wave will form. This is the source of the sonic boom heard when the supersonic plane flies over.